Let's get started. Good evening to everyone. Welcome to week 3 of the live interactive sessions for the course on concrete technology. And I am Sethu Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's get started with the session for week 3. So the overview of the concepts that were covered in week 3. So it was divided into 4 lectures this week, so 7 to 10. And in the first lecture we continued our discussions with aggregates. So we started with aggregate packing density, right? So how the packing density varies for different kinds of arrangement, right? So what affects density, and also we looked at how binary mixtures. For binary mixtures, so we have 2 different sizes of aggregate. So in that case, how will the change in proportion of one size will affect the packing density, right? And then we also looked at a concept called particle interference, right? So when there are 2 different sizes, so there will be some interference that will be taking place between at the boundaries of the 2 different sizes, right? So therefore it will not reduce the amount of voids present to the ideal level, right? So that is the particle interference. And then we also looked at the grading of aggregates. Just give me 1 second, I'll be back. Sorry for that disturbance. Okay, so so we finally looked at the grading of aggregates in lecture 7. So how do we do that, right? So we do basically using sieve analysis, right? So we come up with what is the fraction of the aggregates that are going to be passing through different sieve sizes, or we can also look at it as the percentage of aggregates that are retained on the different sieve sizes, and then we can come up with a grading for the different aggregates. And in the second lecture we looked at fineness modulus and surface modulus, right? So fineness modulus, so based on the proportions of the different size aggregates, so we come up with 2 different modulus. One is the fineness modulus, and another one is the surface modulus. And then we looked at different properties right, of the aggregates, and what are the tests that we do for determining those different properties. And finally we looked at blending of aggregates, right? So we generally have a desired mix or a desired grading that we want, but however what we get will not have that desired grading. So we will have different gradings that will be available to us. So how do we blend those different mixes that are available to us to get the desired blending, right? So that's what we looked at in lecture 8. And then lectures 9 and 10, so they are in module 3. So we looked at so this third module was covering about admixtures, right? So in lectures 9 and 10 we were looking at the chemical admixtures. So in lecture 9 we started with an introduction to chemical admixtures, and then we looked at one type of admixtures, which are the water reducing agents, right? So this water reducing agent helps us reduce the amount of water that is required while maintaining the same workability, right? Or we can also increase the workability for a lower amount of water, right? And then there are different types we saw within those water reducing agents, such as the plasticizers, super plasticizers, and then the hyperplasticizers, right, with varying degrees of effectiveness. And in lecture 10 we covered a higher range of admixtures, starting from retarders, accelerators. So these affect the hydration process, right? So retarders slows down the hydration process, accelerators quickens the hydration process. And then we looked at air entraining agents, viscosity modifiers, then corrosion inhibitors, waterproofing admixtures, and finally the anti shrinkage admixtures, right? So that is the overview of the concepts that were covered in lectures of week 3. Okay, now we'll move on to the questions related to these concepts. So the first question is calculate the optimum volume fraction of coarse aggregate into total solids for a binary mixture. Okay, so we have two um, types of aggregates, coarse and fine, right? And the void ratio is given for the fine aggregates as 0.45 and for the coarse aggregate as 0.4. Okay, so the options are 0.783, 0.568, 0.629 and 0.823. Okay, and as usual I'll create a poll. So once you solve it and you are ready to answer, you can use the poll to answer the question. Okay, any answers? The poll is launched. We have one answer for option A. We'll just wait for a couple more minutes. so we have two votes for option A, 0.783. Okay, now let's take a look at the correct answer. So the right answer is option A, 0.783. So how do we get that? So what we are asked is to calculate the optimum volume fraction of coarse aggregates into the total solids for a binary mixture, right? So we are dealing with a binary mixture, so which contains both fine aggregate and coarse aggregate, right? So what do we mean by the optimum volume fraction? See, there is for the fine aggregate there is one void ratio which is 0.45. For the coarse aggregate there is another void ratio EB which is 0.4, right? So now when we mix these two, for the mixture will have its own void ratio, right? But depending upon how much coarse aggregate you are going to add to the fine aggregate, the void ratio of the mixture is going to vary, right? Depending on the volume fraction of the coarse aggregate that is added. So the optimum volume fraction is that volume fraction which will give you the least void ratio, right? So that's the optimum. So you want to find that least, the volume fraction which gives us the least void ratio of the mixture. Okay, so how do we do that? So we looked at this in the first lecture of week 3, right? So we considered two different cases. One case where we add some coarse aggregate, a little amount of coarse aggregate into the fine aggregate, and then we derived what will be the void ratio of the binary mixture in terms of the volume fraction of the coarse aggregate that is added, right, which is denoted by small x, right? So EA is the void ratio of the fines, and then x is the fraction of the coarse aggregate that is added. So this is the expression that we get when we add solids, coarse aggregates, some small quantity of coarse aggregate into the fine aggregate. Similarly, we looked at the other case where we added some fine aggregates into coarse aggregates, and then we arrived at this expression for the void ratio of the mixture, which was x into 1 plus EB, where EB is the void ratio of the coarse aggregate, right? And x is still the volume fraction of the coarse aggregate in the mixture, right? So we looked at two different cases and arrived at two different expressions. So both are basically for the same binary mixture of fines and coarse aggregates, right? So what would be the optimum volume fraction? It is so we also looked at how this was varying, right? So we looked at as the volume fraction increases, the void ratio was decreasing, right? So and then finally to find the optimum, so it is when these two void ratios are equal. So we equated that, and then we arrived at the optimum volume fraction, which we are denoting it by x star, right? And this was the expression that we got, right? So 1 plus EA by 1 plus EA plus EB, right? So that gives us the optimum volume fraction of the coarse aggregate. So for solving this, we just need the two void ratios which are provided to us. So 1 plus EA is 0.45 and divided by 1 plus EA plus EB, 1 plus 0.45 plus 0.4, right? If you solve that, you will get 0.783, right? So that is the volume, that is the void ratio or the optimum fraction of the coarse aggregate that you have to add to the fines, so that the void ratio is minimum, right? So it has to be 0.783, okay? And that's how we arrive at this answer. Okay, any questions? Okay, for this, just you have to remember this result. For a binary mixture, this is the optimum volume fraction of the coarse in the total solids, right? So so using that, we can arrive at the optimum volume fraction. Okay, so question 2. So we have two statements given. So the first statement says the amount of mortar should be slightly more than the void content in a binary mixture of aggregates to account for particle interference. The statement 2 says wall effect and loosening effect cause additional air voids in a binary mixture of aggregates. So we have four options here. Statement 1 is correct and statement 2 is incorrect. Option B is statement 1 is incorrect and statement 2 is correct. Option C is both the statements are correct, but and statement 2 is also the correct explanation for statement 1. Option D is both are correct, but the second statement is not the correct explanation of statement 1. Okay, you can just take a moment to think about the two statements and pick one of the four options. Okay, the poll is launched. When you are ready, please answer the poll.
So answer is C.
Okay, so you can just put that in the poll. So you'll find the poll within the activities button. Okay, if you open activities button, you will find an option called polls. So within that you can choose one of the four options. Okay, we have 3 votes for option C and 1 vote for option A. Okay, so let's take a look at the right answer. So the right option is option C. Both the statements are correct and the second statement is also the correct explanation for statement 1. So what do we have in the statements? The first statement is saying that we should have more mortar, we should add more mortar than the void content that we have in a binary mixture, right? And why we are doing that is for the particle interference. And the statement 2 is saying that what does the particle interference do, which are the wall effect and the loosening effect. These two effects cause additional air voids in a binary mixture, right? So which means that if we did not consider this effect, we would have certain amount of air voids present, but because of this effects, which is coming from the particle interference, is causing more air voids to be present, right? And that is the reason why we are should be adding more mortar, right? So that both the statements are correct, right? And also the reason is also correct why particle interference is increasing the air voids. It's because of the wall effect and the loosening effect, and therefore option C is the right option. And we saw this in the lecture, right? So if we did not account for particle interference, so then we saw from, as I showed in the previous questions, so we have the two expressions for the void ratio, EA into 1 minus x and x into 1 plus EB, right? So if we plot that, we will get these two straight lines, right? So this is without accounting for the particle interference, right? So that so what we get are these two straight lines. So the void content that we estimate from this expressions will be much lower than what it actually is. So the curved line is what is the actual void ratio in a binary mixture is, right? So how that varies with the different volume fractions. So this is found from experimental results. So that is the actual trend that we will observe. but by ignoring the particle interference effect, we estimate a much smaller void ratio, right? So that's why that's what the statement is saying, because there will be more void ratio than what we estimate in a binary mixture, therefore we should add more mortar, and also the reasoning is correct. Okay, so that's why option C is the right option. Okay, any questions?
No, sir.
Okay, so moving on to question number 3. So we are given three different stockpiles A, B and C, and then we have two sizes of aggregates, 20 mm and 4.75 mm. So we know the percentage passing on these two different sieve sizes for the three different stockpiles. So we also have a desired grading that we want to achieve. For 20 mm it should be 90% passing, and for 4.75 mm there should be 53% passing, right? The question is, what is the proportion of stockpile A, stockpile B and stockpile C respectively to achieve the desired grading by blending aggregates from the above three stockpiles, right? And we have four options: 66.67%, 33.33%, 0%. Option B is 33% from stockpile A, 0% from B, 66% from C. Option C is 66, 0 and 33. Option D 33, 63 and 0. Okay, can again take a minute or two to calculate and answer. Okay, we have two votes so far for option D. Okay, any other answers? Okay, so if there are no other answers, we can look at the answer now. Okay, so the right option is option D. So we have to make the proportions are 33.33% from stockpile A, 66.67% from stockpile B, and nothing from the third stockpile, right? So if we blend it in that proportions, then we will get the desired grading. Okay, so how do we get that? So to do that, so what we will do is try to so we have two different sieve sizes, right? 20 and 4.75, and we know the characteristic of the three stockpiles, how much is passing through these three, and we also know what we require in our desired grading. So we can match what is available to us with the desired grading. So let us just assume the proportion in which we are going to blend is A, B, and C. Okay, proportion A from stockpile A, proportion B from stockpile B, and proportion C from stockpile C. Okay, so in that case, what we will have, so if we take A amount, so then 96% will pass from stockpile A, right? So if we take A, then 0.96 A will pass, plus if we take B from stockpile B, then 0.87 B, plus 75% will pass from stockpile C, right? Now this is how much will pass if we take proportions A, B, and C, but we require it to be 90% passing, right? So it should be equal to 0.9 times of your total value, which is A plus B plus C, right? So this is one constraint. And then the second one is for the other sieve size 4.75. So we have 0.65 times A plus 0.47 times B plus 0.42 times C. This should be equal to 0.53 times A plus B plus C, right? So we have written two equations now based on the information that is given to us, right? So in these two equations we have three unknowns that we want to find. A, B, and C are the unknowns, but we only have two equations, right? So we cannot find all the three unknowns with just the two equations. So what we will do is, let us just assume that A is equal to 1, okay, and then relative to that we will find what should be the values of B and C. Okay, so if you assume A equal to 1, then what happens, the first equation will can be simplified, right? So it will just become 0.96 plus 0.87B plus 0.75C. So that will be equal to 0.9B plus 0.9C plus 0.9, right? So but just substituting the value of A to be 1. So if we simplify this, then we can just write it as, just bring B to one side, minus 0.03B. Okay, so that will be equal to 0.15C. Okay, minus 0.06. Okay, so what I have done is just added substituted the value of A equal to 1 in the first equation, and then simplified it. So then equation 1 here will simplify to this. So similar thing we will do in equation 2 also. So that will become 0.65 plus 0.47B plus 0.42C equal to 0.53B plus 0.53C plus 0.53, right? Substituting the value of A to 1. So again, if we bring B to one side, C to the other side, and the constants to one side, then we will see that minus 0.06B is equal to 0.11C, okay, minus 0.12. Okay, so again, if you substitute A equal to 1 and then simplify it, you will get this equation. The equation 2 will reduce to this equation here, right? So now what do we have? We have two equations left, and then there are only two unknowns, B and C, right? So this we can solve, right? So looking at this, we see if we multiply equation 3 by 2, then we can eliminate B, right? So it is just 2 times of what we have in equation 3, right? So if we multiply equation 3 by 2, then we'll get minus 0.06b equal to 0.3c minus 0.12, right? Now if we add equation 4 and 5, so we can find the value of c, because b will get or basically we just have to equate these two portions, right? So because LHS is same, so RHS we can equate it. So if you equate that, you will find that the value of c is 0, right? If 0.11c minus 0.12 should be equal to 0.3c minus 0.12, that will be equal only when c is 0, right? Knowing the value of c, now we can find the value of b, right? So if you substitute c equal to 0 in one of the equations, so you will see minus 0.06b equal to minus 0.12, so that means b has to be 2. Okay, so now we know all the three values. We have a equal to 1, c equal to 0, and b equal to 2, right? So what we wanted, so we wanted to find the proportions, right? So a is to b is to c is nothing but 1 is to 2 is to 0, or we can write it in another way. So if we divide it by the sum, which is 3, so we can get 0.33 is to 0.67 is to 0, right? So that is in option D, right? So A should be 33.33%, B should be 66.67, and then C should be 0, right? So if we blend the three stockpiles in that ratio, then we can get the desired grading that we require. Okay, any questions? Okay, so I'll just repeat what I just did. So we have the three different stockpiles, and then what is the percentage passing through two different sieve sizes for each of the three stockpiles, and then we are also given the desired grading in which we know what should be the percentage passing for the two sieve sizes, right? So we just assume that we take proportions A, B and C from the three different stockpiles and mix them. So if we do that, the percentage passing through 20 mm sieve will be 0.96 times A plus 0.87 times B plus 0.75 times C, right? So if we blend it in this proportion, then what should that be equal to? It should be equal to 0.9 times of A plus B plus C. So right hand side is what we require, left hand side is what we will get if we mix it in that proportion, right? So those two should be equal, right? That is what we want. Similarly, we write another equation for the other sieve size 4.75, right? So then we have two equations in 3, and then have 3 unknowns, which we cannot solve it in that with just 2 equations, right? So we assume one of the 3 proportions to be 1, right? So we'll assume A is equal to 1, right? So and then we simplify those 2 equations, right? And then it reduces to 2 equations in 2 unknowns. Then we solve that, so we arrive at the values of C and B, right? Once we have that, so we know all the 3 values, A is to B is to C, which is 1 is to 2 is to 0. Normalizing that, we get it as 0.33 is to 0.61 is to 0. Okay, so that's how we find the blending of different stockpiles, right? So to get the desired grading. Okay, so if there is no question, we will move on to question number 4. So here again we are given a particular grading, right? So different sieve sizes from 20 mm to 150 micron, and we are given the percentage passing through these different sieve sizes, right? So the question is, what is the fineness modulus of the given grading of aggregate? So the options are 4.72, 9.68, 2.42 and 14.52. Okay, the poll is launched. Once you are ready, you can answer in the poll. Okay, you can, instead of the chat, you can use the poll. So you'll find the poll within the activities option. Okay, so we have quite a few answers for option A. Okay, so then let's look at the answer now. Okay, the right answer is 4.72, option A. Okay, so how do we find the fineness modulus? So what is fineness modulus? How do we calculate it? So it is nothing but you take the summation of the cumulative percentage retained on the different sieve sizes. Okay, cumulative percentage retained. Okay, and then you divide that by 100, so that will give you the fineness modulus, right? So to do that, what do we know? What do we need is the cumulative percentage retained, right? So how do we get that? So we are given the percentage passing on the different for the different sieve sizes, right? So we can calculate the percentage retained by subtracting the percentage passing from 100, right? So for 20 mm, 100% is passing, which means nothing is retained, so it is 0. For size 10, 80 is passing, which means 20% is retained. For 4.75, 50 is passing, so 50% is retained. For 2.36, 35 is passing, so 65% is retained. For 1.19, 27% is passing, so 73% will be retained, and 75% is retained on 0.6 mm, 90% on 0.3, and then 99% on 0.15 mm, right? So we calculated the percentage retained. Now what do we need to do is find out the sum of all these percentage retained and then divided by 100. So we just have to find the sum. 20 plus 50 plus 65, 73 plus 75 plus 90 plus 99. Okay, and if you calculate it, so it will come out as 472. Okay, so 472 by 100, so which is 4.72, right? So that is the fineness modulus, which is given in option A. Okay, any questions? How do we find the fineness modulus? Okay, so you just have to find out the percentage retained on the different sieve sizes and then find the sum of all the percentage retained, right? So the cumulative percentage retained, and then divide that by 100, so that is your fineness modulus. Okay, so moving on. Question number 5. Which of the following process can be used to determine the silt and clay content in sand? Okay, the options are wet sieving, decantation, washing, NaOH treatment. Yeah, the poll is activated for question 5. Okay, any other answers? We have a couple of votes for option B, and there is one answer in the chat for option A. Okay, 3 votes for option B. Okay, then we can look at the answer now. Okay, so the right option is option B, decantation, right? So wet sieving we use for coarse aggregates, right? So it is not for silt and clay. Washing is when you have anything soluble, then you could remove that by washing, right? So if it is not the case, then washing will not be helpful. And NaOH treatment is for detecting the organic impurities, right? So that's when we use for NaOH. So for this fine materials like clay and silt, so we go for the decantation process. So what is the decantation? When you have two materials or two substances that are not soluble in each other, right? So then you can separate them out using decantation because of their different densities. So they will separate out, and then once they are separated out, you can remove one material or one substance from the other using so that's what decantation is, right? So because here fine silt and clay are finer, so they will and they are not going to mix with sand, so we can separate those out using the decantation method. Okay, so question number 6 is, which of the following water reducing agents show steric effect? Option A is lignosulfonate, option B is sulfonated naphthalene formaldehyde, option C sulfonated melamine formaldehyde, option D is polycarboxylate ether. Okay, the poll is launched. Okay, so we have a couple of votes for option D and one for option A. Okay, any other answers? Okay, so we can look at the answer now. It is option D, polycarboxylate ether, right? So among the four, the first, the sulfonated type of water reducing agent. So they, what do they do? So their mechanism of action is, so they dissociate the sulfonated group. That part will dissociates, right? And then you get the negatively charged sulfate ion. So that will get adsorbed on the cement particles, so giving the cement particles a negative charge, and that negative charge will cause the repulsion between the particles, and hence the uh, dispersion occurs, right? So that's how they work. Whereas the polycarboxylate ethers, they work differently. So where they have this polymer group, right, the polyether, so which is a larger group compound, so which does not dissociate, right? So that will be there, and then so this also gets adsorbed. This polycarboxylate ether, it also gets adsorbed on the surface of the particles, but they do not impart any negative charge as does the sulfonated type, right? So instead, what do? Because of their larger polyether part that is getting adsorbed, the effective size of the cement particles are increased, right? And then this increased size will push the cement particles which were together before away from each other, right? So that is what we call as the steric effect, right? And that is shown by this polycarboxylate ether, right? So that is how that is the mechanism that we observe from the polycarboxylate ether type of water reducing agents, right? So therefore the right option is option D. Okay. So question number 7, which of the following can be waterproofing admixture? Options are cellulose ethers, calcium nitrite, calcium chloride, and steric acid. Okay, we have 3 responses for option D. Okay, let's take a look at the answer now. Okay, the right option is option D, steric acid, right? So we are talking about waterproofing admixtures, right? And for this we so we use these damp proofers based on different fatty acids like oleic, caprylic, and steric acids, right? So these types of fatty acids, right, they help us in waterproofing, right? So in waterproofing, what do we mean by that? It is, so we reduce how much water is going to be absorbed by this cement. So what to do that, we have to reduce the permeability, right? So we should not we should reduce the amount of water that's going to enter into the concrete. So for that we reduce the capillary absorption, right? So to do that, the fatty acids like the oleic, caprylic and stearic acid, so they help us block these capillary pores, and therefore act as a water proofing admixtures. Okay, whereas the others are for different purposes, right? Like calcium nitrate is for corrosion inhibition, calcium chloride we use as accelerator and so on, right? So it is D which is the waterproofing admixture. Okay, so question number 8 is we have a sample of concrete which has 28-day compressive strength of 40 MPa and a slump value of 80 mm. Keeping the slump values the same, what would be the best alternative among the given options to further increase the 28-day compressive strength value? So we have 4 ways. One is by increasing the cement content, by increasing the water to cement ratio, by increasing the water content, by adding water reducing agent. Okay, so we have a couple of votes for option D. Okay, any other answers? Okay, so the right option is option D, right? So that is correct. Option D is right, by adding water reducing agent, but it's not precisely what we are looking for, right? So can anyone identify what is wrong with option D? So for this question, among the 4 options, D is right, but it is not precisely stated for the problem requirement. Can anyone identify that? You can use the chat or unmute yourself and answer it. So it's not just enough to add the water reducing agent for what is asked in the question. So we need to do something more also. So what is the question saying? It is saying that the slump value has to be maintained, right? So in other words, the workability should not be affected, right? So workability should be the same, but we have to increase the compressive strength. So we need to have more strength for the same workability. So what I am saying is, among the four options, so as you have said, option D, so that is correct. That is the best of the four options, but it is not enough to just do what is said in option D to achieve higher strength. So you can use the chat, or you can unmute yourself and then correct that option. Anyone? Yeah, W by C is increased for workability, but here we don't want to increase the workability. So we want the workability to remain the same, but the strength has to be increased. So we don't want higher W by C. So we'll get more strength when your W by C is smaller, right? Okay, so then let me explain. So D is right, we add water reducing agent, but in addition to that we also have to reduce the water content, right? So if you remember this graph, so we have two lines given here, so which tells us what is the workability versus the water content. One is without any water reducing agent or super plasticizer, and the other one is with some super plasticizer added, right? So what do we have here? So if you want to increase the strength but maintain the same flow, right? So if you draw a horizontal line, that means all those points the flow or the workability is the same, right, for different water content. So when you have to increase the strength, so you have to not only reduce add super plasticizer, but also reduce the water content, right? So for example, the example shown here is going from somewhere like 205 to kilogram per meter cube to somewhere around 160 or 165, right? So right, for the same flow, so the workability is maintained the same, but we have to reduce the water content and add the super plasticizer to increase the strength, right? So if you just add the super plasticizer without reducing the water content, what happens? Here workability will increase. It's not going to increase your strength, just it will become more, the cement paste will just flow more, right? It's going to be more workable but not necessarily have higher strength. So to achieve strength, you have to add the super plasticizer and also reduce the water content, right? So then only your W by C ratio will go down and your strength will increase, right? So that's why I said D, what is stated in D is not precise, right? It is not complete. So it's not just adding water reducing agent, but also reducing the water content. Okay, any questions? Okay, moving on to question number 9. So we are given two columns. In column 1 we are given some admixtures, and in column 2 we are given some effects. So we have to match the right admixture with the right effect. Okay, so we have lithium salts, winsol resins, nitrite formate, and polycarboxylate ether as the admixtures, and then 4 effects: improves the freeze thaw resistance, improve workability at same water content, resist expansion due to alkali aggregate reaction, and accelerate the formation of etching, right? So 4 different matchings are given. The right matching has to be selected. Okay, the poll is launched. When you are ready, you can use the poll. Okay, there is a question in the chat. The working of water reducing agent and super plasticizer is same or different? So they are just two different terminology. They are used for the same type of admixture, right? So water reducing agent and super plasticizer are nothing but the same thing, right? So they are just different terms that we use, but they are going to they are the same type of admixture. Okay, we have two votes for option D. And just wait for one more minute. Okay, any other answers? Okay, the option D in the previous question is alternately said about super plasticizer. Okay, yeah, so here we are saying water reducing agent in option D, which is the same as super plasticizer. They are both referring to the same thing, right? So sometimes we use plasticizers, sometimes we use water reducing agent. It's just different terminology referring to the same admixture. Okay, water reducing agents and plasticizers are the same thing. Okay, that's why in the graph we have written as super plasticizer. It is the same as it is also a water reducing agent only. Okay, is that clear? Okay. Okay, now let's take a look at the answer for 9th question. So the right option is option D. Okay, so what is option D? So 1C, 2A, 3D and 4B. So lithium salt is nothing but is going to help us prevent the alkali aggregate reaction, right? So we one of the requirements of the aggregates is that they should be inert, but in some cases they do react, right? For example, with alkalis, right? So in that case, lithium salts can help us prevent the alkali aggregate reaction, right? So that is given in option C. It resist expansion due to alkali aggregate reaction. So winsol resin is an air entraining admixture. Therefore, it helps us improve the freeze thaw resistance, right? Especially in cold weather. And then nitrate formate. Nitrate formate is an accelerator, right? And therefore, it accelerates the formation of ettringite. So that is mapped with option D. And we already saw polycarboxylate ether is a type of water reducing agent, right? And therefore, it improves the workability at the same water content, right? If we maintain the same water content and add the water reducing agent, then workability will be improved, right? So that is option B. So that matching is given in option D. 1C, 2A, 3D and then 4B. Okay, so that is the right option. Okay, so question 10. So we are given 4 statements here. Statement 1 is sulfonated plasticizers are more effective in high C3A cements. Statement 2 is better dispersion ensures high early strength with use of plasticizer. Statement 3 is viscosity modifier admixtures lock the water, cementitious material and sand, which results into increase in the bleeding in case of underwater concrete structures. And the fourth statement is anodic inhibitors increase the corrosion threshold by making the passive layer more stable. So the question is, which of the above statements are correct? So the options are 3 and 4, 1 and 3, 2 and 4, 1 and 4. Okay, the poll is launched. Please take a moment to think about the four statements and then answer which of them are correct. We have one vote for option B. Okay, one vote for option B, one vote for option C. Any other answers? Okay. Okay, there is a 50-50 situation. 2 votes for option B, 2 for option C. Okay, And then I think we can look at the correct option now. Okay, so the right option is option C, 2 and 4. Okay, so probably those who selected B did it in a hurry, because it is the opposite of what is the right answer, right? 1 and 3 are the incorrect statements and 2 and 4 are the correct statements. Okay, probably you didn't read the question correctly. It is asking to pick the correct statements, right? So 2 and 4 are the right statements, 1 and 3 is the incorrect. Okay, so let us see why those are the right, and why 1 and 3 are wrong. So statement 1 says that sulfonated plasticizers are more effective in high C3A cements, right? So if you remember from our first two sessions, we looked at what happens in cements with high C3A, right? So we looked at one particular situation, right, called the sulfate attack, right? In those cases we use cement with less C3A. Why? Because C3A reacts with sulfate, right, and therefore it results in expansion, right? So volume expands. So that is what we saw in the sulfate attack, right? So similarly the sulfonated plasticizers also react in a similar manner with C3A. Therefore if we have cements with high C3A, then the sulfonated plasticizers will be reacting with the C3A, and therefore their effectiveness as a water reducing agent will come down, right? So they will be, because they will be reacting more with the C3A, they will not be doing their water or producing their water reducing effect, right? So therefore statement 1 is incorrect, which is saying that it will be more effective. Actually it will be less effective when C3A is high for sulfonated plasticizers. Okay, statement 2 is a better dispersion ensures high early strength with the use of plasticizer. It is true, right? So when we use plasticizer or water reducing agent, so we are going to get more dispersion, right? So the particles are going to be away from each other, so which means that there is going to be more area or more surface area that is going to be exposed, right? So there is more area that is available for the hydration process to occur, right? So water can come into contact with a larger area of the cement particles, which ensures that more hydration can take place, right? When more hydration takes place, the strength that we are going to gain is going to be higher, right? So therefore better dispersion is going to ensure that we are going to get high early strength, and when we are using the plasticizer. So statement 2 is correct, right? Now statement 3 is viscosity modifier admixtures lock the water, cementitious material and sand, which results into increase in the bleeding in case of underwater concrete structures. So now there are two parts in this. So first one is just talking about the action, the mechanism of how the viscosity modifier is going to work. So right, it's going to lock the water, cement particles and the sand together, right? So that is correct. So when we are going to use the viscosity modifier, this is what is going to happen. So all the three components are going to come together, right? So that part is correct, but what it is saying is in the second part, it results into increase in the bleeding in case of underwater concrete structures, right? So that part is incorrect, right? So what is bleeding? So when you have excess water that is not chemically, that is not chemically bonded with the cement material, it's not reacting, it's present as free water, so that's going to come out to the surface of the concrete, right? So that is the bleeding, that's when we call bleeding, right? When we are using the viscosity modifier, we are saying that it is not going to happen because the water and the cement materials and the fine aggregates, they are going to be locked together, so it is not, the water is not free to come out, right? So the bleeding will actually reduce when you are going to use the viscosity modifier. Therefore statement 3 is incorrect in saying that the bleeding will increase, right? And statement 4 is about the corrosion inhibitor. So anodic inhibitors increase the corrosion threshold by making the passive layers more stable, right? So that is true, that's how the anodic inhibitors work, right? So this passive layer, so what is that? It going to, these anodic inhibitors, they are going to produce some oxide layers like ferric oxide, right? So that is going to cover your metal surface, right? and where this anodic reaction takes place, so that site will be covered by a passive oxide layer, which will not expose the metal for further corrosion to occur, right? And therefore corrosion threshold is going to increase, right? It's going to be more difficult for corrosion to occur when we have this passive layer, which is also a more stable oxide layer. So therefore this metallic surface is not going to be more exposed, and therefore corrosion will reduce, right? So therefore statement 4 is also correct. So among the four, only statements 2 and 4 are correct, and 1 and 3 are incorrect. So therefore the right option is option C, 2 and 4. Okay, any questions? Okay, so moving on to question number 11. Which among the following arrangements has the highest packing density? Options are simple cubic, body centered cubic, face centered cubic. Option D is all the three have the same packing density. Okay, we have one vote each for option A and option B. Okay, we have 2 votes for option A and 1 each for option B and option C. Okay, so let's take a look at the answer now. The right option is option C, face centered cubic, right? So that is going to have the highest packing density among the 3 arrangements, right? So in fact, if you look at the packing density, it is lowest for simple cubic, which is around 0.52. For body centered, it will be 0.68, and for face centered, it is the highest with 0.74, right? So that is the right option. So how do we arrive at that? So you can derive it, so you can show that it is in fact equal to those values, but you can think of it without doing those calculations and you can see why it is higher for face center. So in a simple cubic arrangement, what do we have? You take a cube, okay, of some side length a, and then you have assume spherical particles, and then these are arranged or placed on the corners of the cube, right, such that the 2 adjacent particles are going to be touching each other, right? So that is the simple cubic arrangement. So what happens is, when you arrange it in such a manner, so 1/4 the volume of each particle is going to be lying within that cube, okay, and therefore there are 8 corners in a cube, right? So effectively it is like having a single spherical particle within the cube, right? It is like effective in like having equivalently having one particle within the cube, because each corner is going to contribute, each particle in a corner is going to contribute 1/4 of its volume to be present inside the cube, right? So it's like having effectively one spherical particle inside the cube. That is in a simple cubic arrangement. Now let's come to the body centered cubic arrangement. Here what do we have? So within the center of the cube we have a single spherical particle, and then there are one spherical particle on each corner of the cube, right, such that the particles on the corner of the cube is going to be touching the particle in the center of the cube, right? So that is the body centered cubic arrangement. So in this, if you look at it, there is a single particle within the center, right? So its volume is completely within the cube, and again there is going to be 1/4 of the volume from the corner particles, right? So again there are 8 corners, so therefore effectively it is like having 2 cubes, 2 spherical particles inside the cube, right? So that is the body centered cubic arrangement. When you come to face centered, so again, instead of having one particle in the center of the cube, we have particles along the sides of the cube, right, such that particles on 2 sides are going to be touching each other, right? So it is like contributing half. So the particle on the each face is going to have half of its volume inside the cube and half of its volume outside the cube, and then again there are going to be particles on the 8 corners, right? So 2 faces is going to is like having one is going to provide a volume equal to 1 sphere, right? And there are 6 faces, so you will get effectively 3 spheres inside the cube and then 1 sphere from the 8 corners, right? So it is like effectively having 4 particles inside the cube, right? So if you look at it in simple cubic, we have 1, in body centered we have 2, in face centered we have 4 particles, right? So therefore the density in the face centered must be higher, right? So if you just draw these arrangements, and then you will be able to see why that is so, right? You will be intuitively be able to see that in a face centered you will have highest density, and in fact you can go on to show that it is actually 0.52, 0.68 and 0.74, right? I'm not doing those derivations here, but you can show that numerically as well. Okay, so that's why it is face centered cubic arrangement that has the highest density. Okay, you can try that, and if not, you can let me know. We can look at it in the next session. Okay, so moving on to question number 12. A small quantity of coarse aggregate, so which is, we are going to call it as 1, is added to fine aggregate, which is 2, keeping the packing of aggregate 2 undisturbed. Okay, if the proportion of the coarse aggregate 1 is assumed to be y, and void ratio of the fine aggregate is E2. The void ratio of the resulting mixture is given by the expression. There are four options: y into 1 plus E2 minus 1, 1 minus y times E2, E2, and none of the above. Right, so basically we are looking at a binary mixture of a fine aggregate and a coarse aggregate, right? And for the fine aggregate the void ratio is E2, and we are going to add y proportion y of coarse aggregate into this fine aggregate. So we want to know what will be the resulting void ratio of the mixture. Okay, if you remember, this is what we started out with this session, right? We looked at the binary mixture. So there I actually gave the expression. So if you remember that, you can easily answer it. Otherwise you can take a moment to answer which of these is the right one. So if you add y amount of coarse aggregate into a fine aggregate, right, what will be the void ratio of this binary mixture? Okay, any answers? Okay, we have one vote for option A. Okay, one for option B. Okay, I'll give one more minute. Okay, any other answers? Okay, let's take a look at the right option now. So we have one for option A, one for option B. Right, so this is expressions given in options A and B are the same expressions that I showed in the first question as well, right? So if you just go back, so I gave that EA into 1 minus x and then x into 1 plus EB, right? So same expressions, just the notation is slightly different now, right? So here we are using y for the volume fraction instead of x, right? And 2 represents the fine aggregates instead of a, right? But they're different. They belong to two different cases. One is for adding fine aggregate, a small quantity of fine aggregate into coarse aggregate. The other expression is for adding a small quantity of coarse aggregate into fine aggregate, right? So in this question we are looking at the case where a small quantity of the coarse aggregate is added to fine aggregate, right? So for that case, the right option or the right expression of the void ratio of the mixture is option B, 1 minus y times E2, where E2 is the void ratio of the fines. So how do we arrive at this? So let's derive that expression. So let us assume that capital V represents the bulk volume, okay, of the fine aggregates, okay, which is aggregate 2. And then let us also assume that small V1 and V2 be the solid volumes of coarse and fine aggregates. Okay, let's just defining some terms. So V is the bulk volume of the fine aggregate, and V1 and V2 are the solid volumes for the coarse and the fine aggregates. Okay. Now what do we want? Our interest is in finding the void ratio of the mixture, right? So void ratio is represented by E for a given fraction, volume fraction of the coarse aggregate into the fine aggregate, right? So we want to know what is the void ratio, right, denoted by E of y. So if you remember, the definition for the volume void ratio is nothing but the volume, the total volume divided by the solid volume minus 1, right? So the total volume, what is it? So it is nothing but the bulk volume of the fine aggregate and plus the bulk volume of the coarse aggregate, because there are only two aggregates in this mixture, right? So for the bulk volume of fine aggregate, we said it is V, whereas for the coarse aggregate it will be V1, because we are adding a small volume, small quantity of the coarse aggregate. So the bulk volume is going to be almost the same as the solid volume. So the total bulk volume is V plus V1, right, divided by the solid volumes. So V1 plus V2, that is the total solid volume, and this minus 1. So this is by definition what is the void ratio, right? So total volume by the solid volume minus 1, right? So now we can rewrite it as V by V1 plus V2 plus V1 by V1 plus V2 minus 1. I have just split this first term into two terms, V by V1 plus V2 and then V1 by V1 plus V2, right? I have just split it into two different terms, and then I'm going to multiply the first term that we have here by V2 and then divide it by V2, right? So I'm just manipulating it. So V by V2, right, and then it can be written as V2 right? So the other two terms are going to remain the same, right? So what I have done, I have multiplied V2 and divided by V2 for the first term that I have here. So it becomes V by V2 times V2 by V1 plus V2. The other two terms remain the same. Okay, so going to the next line. So here, so we can further modify this first term, right? So it is v by v2, so that part is remaining the same. So v2 by v1 plus v2 can be written as 1 minus v1 by v1 plus v2, right? So this will give us exactly the same thing, right? So if you simplify it, this will be exactly whatever is in the bracket will be become v2 by v1 plus v2, right? So if you take v1 plus v2 minus v1 by v1 plus v2, that will be v2 by v1 plus v2. I'm just rewriting that in this form, and the other two terms will still remain the same, right? I'm not changing that. Now what is this v1 by v1 plus v2? So v1 is the solid volume of the coarse aggregate and v2 is the solid volume of the fine aggregate. So v1 by v1 plus v2 is nothing but the proportion of the volume fraction of the coarse aggregate, the solid volume of the coarse aggregate in the total solid volume, right? So the total solid volume is v1 plus v2, and the proportion for the coarse aggregate in the total solid volume is v1 by v1 plus v2, and in the question that is given as y, right? So the proportion of the coarse aggregate is assumed to be y, right? So this particular fraction v1 by v1 plus v2 is nothing but y as given in the question, right? So if we just rewrite that, so v by v2 times 1 minus y plus, so similarly this is also exactly the same, v1 by v1 plus v2, that is y minus 1. Now we have three terms, v by v2 into 1 minus y plus y minus 1. So if we take 1 minus y to be common, right? If we take 1 minus y as common, then what we end up with is v by v2 minus 1, right? So y minus 1, if we take 1 minus y common, we will be getting minus 1, and for the first term we get v by v2, right? So now what is v by v2 minus 1? So v is the bulk volume of the fine aggregate, v2 is the solid volume of the fine aggregate. So bulk volume by solid volume minus 1, that is nothing but by definition is the void ratio, right? So that's what we started with, right? So total volume by the solid volume minus 1 is the void ratio, and this is for the fine aggregate, right? So v is the bulk volume for fine aggregate, solid volume for fine aggregate. So this particular term is nothing but the void ratio for the fine aggregate. So E of y can be written as 1 minus y times, so the void ratio for the fine aggregate, again in the question it is given as E2, right? So I'm just replacing v by v2 minus 1 as E2, right? So the final expression that we have for the void ratio of the mixture is 1 minus y times E2, right? So which is exactly what is given in option B, 1 minus y into E2. So if we add y, if y is the volume fraction of coarse aggregate into added into a fine aggregate, then the void ratio of the mixture will be 1 minus y times E2, right? So that's how we find it. Okay, any questions? Okay, this was done in the lectures also, so if you can go back to the lecture also to find to revise that. Okay, if you have any doubts, you can ask. Okay, so there is nothing now, we'll move on. So question 13, for a binary mixture, which of the following is true for the packing density? So we have four options. Packing density increases with addition of the second size, packing density decreases with addition of the second size, packing density increases initially but start decreasing after a limit, packing density remains constant. Okay, so which of these is correct? Okay, there is one vote for option A. Okay, one vote for option B as well. Okay, any other answers? Okay, so we have one more vote for option C. Okay, so we have one vote each for A, B, and C. Alright, so let's take a look at the correct one. So the right option is actually option C. Right, so it is the packing density is does not have a monotonic relationship with the volume fraction of one size in the other. Right, so it is actually it increases as we look at the graph here, right? So it shows the packing density as a function of the volume fraction. So it could be either A in B or B in A. So in both cases it is so it will initially increase, right, reach a maximum packing density at some optimum volume fraction, and then it will start decreasing, right? So if when you come from the other way also, it is going to be the same, right? So either when you have one size A, you add some proportion of B into it, right? At some point it will be higher, and then when you add more B, it is going to decrease, right? So it is, that's how we see it. So this is similar to what we saw for the void ratio. So in the case of void ratio, we had the opposite effect, right? So it will initially be higher when you have a single sized particle. So when you add the other size, it will decrease, reach a lowest point, and then it will start increasing as you add more of the second size, right? So that's what we saw for the void ratio. So for the packing density, it is just the inverse of that, right? So as the void ratio goes down, your packing density is going to go higher, but the trend is going to be the same, right? So it is going to increase by first reach a maximum, and then it's going to decrease. It's not going to keep on increasing or decreasing, right? So that is option C. Okay, question 14. For single sized particles of size 300 micron, fineness modulus will be options are 0, 1, 2, and 3. Okay, so we have only a single we have uniform sized particles, everything is of 300 micron. So what is the fineness modulus in that case? We don't have a distribution, just a single value. Okay, we have one option for option D. Okay, one vote for option A. Okay, any other answer? Okay, one vote for option C. Alright, so let's take a look at the answer now. So the right option is C, 2. The fineness modulus is 2. So how do we do it? So there is a simple way. You don't have to do any calculation. When there is a single sized particle, so the fineness modulus will always be the sieve number corresponding to that sized particle, right? So remember that the smallest size of the aggregate, 75 micron, so that has the sieve number of 0, and then for each higher size the sieve number increases by 1, right? So 75 micron is 0, then 150 micron is sieve number 1, 300 micron is sieve number 2, right? So when you have single sized particle, as is the case in this question, which is 300 micron, so the fineness modulus is equal to the sieve number itself, right? And the sieve number corresponding to 300 micron is 2. Therefore we can directly answer that the fineness modulus will be 2, right? So that is for answering it. But how do we understand it? So what is this fineness modulus representing? It is basically representing the average particle size, right? So when you have a mixture of different sized particles, so different proportions of different sized particles, so we are just this fineness modulus is a way of defining the average particle size, right? So average particle size not in terms of the size itself in like millimeters or centimeters, but in terms of the sieve number, right? So we have the different sieve numbers 0, 1, 2, 3. So we are going to use the average sieve number, right? So that's what the fineness modulus is. So when you have all particles belonging to to the same size, then the average size is equal to that single size itself, right? So every value is equal to the same value, which means that the average is also equal to that same value, right? So for 300 microns, if you have 10 particles of everything as 300 micron, then the average size is also 300 micron, right? So the average sieve number is nothing but the sieve number corresponding to that particular size, and for 300 micron the sieve number is 2. Therefore the fineness modulus is 2 for the size for single size particles of 300 micron. Okay, any question? Okay, so if there is no question, moving on to question number 15. Which of the following property of aggregate is related to the volume changes due to wetting, drying, thermal and frost action? Options are bulking, soundness, thermal conductivity and particle size. Okay, there is one vote for option B, soundness. Any other answers? Okay, one answer for option A, bulking. Okay. Okay, any other answers? Okay, so let's take a look at the right option now. So the right option is option B, soundness. So if you remember, we also have talked about soundness of cement, right, which is also related to volume changes, right? So the sudden volume changes which is called which is the property of soundness, right? So when there is high volume changes, so in that case we call the cement to be unsound, right? So similarly for aggregates also, it is this change in the volumes due to different environmental action. So that is the property that we call as soundness, right? So you may confuse it with bulking, but bulking is more for the volume increase in sand, right? So that is specifically for sand, which we call it as bulking, whereas soundness is for the volume change because of the different environmental actions on the aggregate, right? So that is the soundness property. Thermal conductivity is because of the heat expansion, okay, expansion because of thermal activity, right? Therefore the right option is soundness, because it's about volume change because of wetting, drying, thermal and the frost action. Okay, because of these different environmental uh, action effects, the resulting change in volume is called soundness. Okay, any questions? Okay, so with that question, we conclude this particular session. Okay, if you have any doubts, you can ask. I'll just wait for a couple of minutes in case you have any queries or doubts. Okay, if you don't have any questions, you can feel free to leave the session, and we'll meet again next week in the same time. Okay, thank you for attending.